We were doing the normal distribution, and the standard normal distribution is a special case. The mean is 0, the standard deviation is 1. And it's a way to, we used to have to do that to do anything with the normal distribution because we're looking it up in a table, and you've only got one table. What it's used for now is a way to go from one normal distribution to another. You standardize one, and then you can unstandardize it to something else. So that if I have this distribution with a mean of 50 and a standard deviation of 10, I go up one standard deviation to 60, up 2 to 70, down 1 to 40, down 1 to 30. And if I want to standardize a value from this one, I put it into the standardizing formula. This says how far is a value x from the mean measured in standard deviations. I have a new ruler for every normal distribution, and the ruler is the standard deviation. So it's marked in standard deviations. So that if I had 55 in this one, to standardize it, and this formula is always the same, and all it does is figure out how far from the mean and how many standard deviations that is. So this is 0.5 standard deviations. Here, that comes to right there in the standard normal distribution. So 55 goes to there. And if I want to convert it to another distribution, this one with a mean of 40 and a standard deviation of 5, I just go backwards. So that if I take this formula and solve it for x, purely all it is, multiply by the standard deviation, move the mean over. This says this value is half of a standard deviation above the average. I take half of this standard deviation and add it to the mean. X is equal to 40 plus 1/2 of a standard deviation. This thing moves from here to there, standardized, and then I convert it to another distribution. This is the way that SAT scores are done. They have SAT scores in testing centers all over the country. They do it on the computer. Every group that takes the test has a different mean and standard deviation. To make them nationwide, they take all of them, standardize it, and then convert it back to the mean and standard deviation they want. So that this now is more of a passing through point. But it's an important passing through point because I can take any normal distribution and convert it to any other normal distribution. Right, on this sheet, you still got this sheet? Number 5, the average SAT score in 2023 for the District of Columbia was 977 with standard deviation 249. In Wisconsin, the mean is 1294. And the standard deviation is 180. The national average was 1124 with a standard deviation of 94. Every group has a mean and a standard deviation, and I need to put them all on the same basis. Suppose someone in DC gets a 1050. Any kind of standardized test, when they send you a score, they give you a percentile. And the percentile is how many people scored less than you did and how many scored above. So if you got a 50 percentile, that means half were below, half were above, and basically you're right at the average. So all of these things have to be converted to a standard basis. But here, this score is 1050. And I need to standardize it. I need to know where it is in this distribution. So I need a z-score. This is where the empirical rule comes from. How many standard deviations? The mean is 0, standard deviation is 1. That's where the -1, +1, -2, +2 come from. 2 standard deviations up, 2 down. The standard deviation is 1. So I have 1050 minus 977. And I divide that by 249. Where is this score relatively in a standardized distribution? That score is 0.29 standard deviations above the average. The z is 0.3 basically. So if I put this on a 0-1 scale, this is higher than the average, but it's not a whole lot higher than the average. This is 0.29. And on the z, 0, 1, 2, -1, -2, (977) plus 1 standard deviation. I add these two, 16, 1226. The 1226 corresponds to the 1. 977 corresponds to the 0, and that score is 0.29 up. So that's its position in the 0-1 scale. The national average was 1124, and the standard deviation was 94. I want to know where this 0.29 is, where this score of 1050 out of DC is in relation to the national average. Turn the formula around, and I get 0.29 times the 94 plus 1124, so that now I've got it on the scale of 1124 and 94. So if I do this calculation, 0.29 times 94 plus 1124, it's going to give me a score a little higher than the average. It's going to be 0.3 of 94 above the average. So it comes down into here. So I've taken that score, converted it, and put it on the national average. This is a common thing when you have distributions from different groups and you're trying to get them on a common basis. You are literally standardizing the scores, standardizing the distributions, which is why it's called standardizing. Also in these things, look at how big the standard deviation is here compared to here, compared to here. This is like an expanding scale. This one is like this. The next one comes in here, the next one's this wide. So not only have I moved the average to a common center, but I've adjusted those standard deviations. My scale of standard deviations is the 249, 180, and the 94. And when I move between them, all I'm doing is saying, here's the standard deviation. Here I am on this scale. If I have a different standard deviation, what is 0.29 of the new standard deviation? All right, look at the other part of this. 1300. Both of them got a 1300. Which one had the higher score? Convert 1300 to the z-score based on the DC mean and standard deviation and the Wisconsin mean and standard deviation. That'll tell you where they are relatively when compared directly. Find the z-score for both of those situations. And the z is always just what's the difference from the mean and how many standard deviations is it? X minus the mean divided by the standard deviation. The z-score for the first one is 1.29. It's more than one standard deviation up, a little bit more. What's the z-score for the second one from Wisconsin? What's the z-score for the second one? 0.03. Which one did better relatively on the test, on the SAT test? On the standard normal, where is 1.29 compared to 0.03? The Wisconsin score is hardly above the average, where the DC score is more than one standard deviation above the average. I can tell which one did better relatively. What's the percentile? What percent of the normal distribution is less than 1.29? Just guessing at it. Don't need a table or anything. 0, 1, 2, minus 1, minus 2, and I have a 1.29. Approximately, what's the percentile? Normal distribution, 95 here to there, 68, 1 to minus 1. I've got 68 here, and this is 16 because it's half of what's left. This is 84. This score has to be in at least the 84th percentile. If you put it in Excel, we can use the standard normal equals norm dot s dot dist. This is different than the norm dot dist because in the norm dot dist I had to give it the mean and the standard deviation. Now I've got a mean and a standard deviation, but they're 0 and 1, so I don't have to put them in. It's the standard normal. And if I do 1.29, 1.3, and it's always cumulative, this score is in the 90th percentile. What's the 0.03 percentile? What's it gotta be minimum? This one's right here, 0.03. What's the minimum percentile it has to be? 50, because it's 50. And we're just above that, so that with the norm.s.dist, norm.s.dist, I have that score. It's still cumulative. That didn't go well. What did it do?
You put a little negative in front of it.
I did put a negative in front of it. That didn't look right. So this one is, the score is in the 51st percentile, just barely above the average. This is a way to go between normal distributions. It used to be the way we had to do everything. You wanted a probability for 1300, you had to convert it to a z-score and look it up in the table. Now, it's not a big deal. We can put in whatever mean and standard deviation we want and let the computer do it. And what the computer actually does in this case is standardize it and look it up. It's doing the same thing we were doing the hard way, because that's the easiest calculation to make, but we don't need to know what's going on in there anymore. Convert both of those back to the 1124 mean and 94 standard deviation. We want it to go back to the national basis. So both of those z-scores, 1.29 and 0.03, we already did the 1.29, didn't we? Didn't calculate it out. What is the relative position of these scores? 1124, 94. What is the score that's 1.29 standard deviation above the average and 0.03 above the average on this scale? Each one, you take how many standard deviations up is it? This one is 1.29, and now the standard deviation is 94. I add that to 1124. What's the score on the national basis? What is the 1.29 score? 1,245. 5. How about the 94? Not the 94, the 0.03. It's going to be much closer to that 1124 average. 0.03 times 94 added to that average 1124. Here the one is 28. 943. 2 plus 8, that's 14. 3, that's 2 decimals, 1.1124 plus 2.82. 1126.82. And if you look up these adjusted scores, 1245 and 1126, to find what the percentile is, it's going to be the same percentile that we had before in each one. The higher one's going to be in the 90th percentile, the lower one's going to be in the 51st. So that all this is a way to basically shuffle things around, and it's different here. You make it the same there, and then you can spread it back out again. Then look at the last problem. I've been telling you about the empirical rule. 68% between -1 and +1, 95% between -2 and +2. I lied to you. That isn't actually correct. How wrong was I? What are the real cutoff values for 95% and 68%? And how are you going to calculate it? And you can use the standard normal distribution. I said 68% between -1 and +1, 95% between -2 and +2. How are you going to verify that? You can't look up the normal distribution from here to there. All you can do is get the area, the percent, the probability from the left. So how are you going to check the 95% business? What do you have to look up to get 95%? I got 95% in the middle. I can only go from here way back at negative up to that lower limit, which I said was minus 2. What's the area to the left of 95% in the middle? 95 in the middle, what's on the outside? 5%. What's in half of that? Half of it here and half of it there. 2.5. So what am I going to look up in Excel? And this is going to be norm.s.inv. I want to go from a probability to the number that does that. If you put in 0.025, 2.5%, what do you get back out? Negative 1.95. What did I say it was? 95% in the middle. What's the low end? Negative 2. How close is minus 1.96 to negative 2? Pretty close. So I didn't lie too badly. What's the next one? $68 in the middle, but I can't look up 68 in the middle. I have to look up from minus infinity up to something. What percent of the distribution is to the left of 0.68, 68%? How much is not in the 68? 100 minus 68 is 32. How much is in each end? This is 16. I need to look up 0.16 equals norm.s.inv 0.16, negative 0.99. That's pretty close to minus 1. What about checking the other ends? I want to check this. This should be about, or plus 1. How do I look this up? What's the area to the left of that point on the curve? 68 in the middle. Half of that on each side. I got 16 here, 68 there. How much do I have coming up? 84. So I need 0.84. Norm.s.inv 0.84. I got exactly the same as I did with the 16, except it's not negative. This is perfectly symmetrical. So this one, this is minus 0.99 plus 0.99. What am I going to look up for that? The upper end of the 95%. 95% in the middle, and I have to come from the far end of negative infinity. What probability, what's the percent of area to the left of that mark right there? This is 95%. How much is outside? 5. How much is half that? 2.5. So I have 2.5 here. Outside of this, add it to the 95. What do I look up on this end? I have to look up 97.5. And I'm going to get the same thing as I got for 2.5 on the other end, except it's going to be positive. Equals norm dot s dot inv 0.975 and I get the same thing at 97.5 as I got at 2.5. So this is the empirical rule. This is where it comes from. 95% between minus 1.96 and plus 1.96, which I said was 2 and minus 2, and 68% between minus 0.99 and plus 0.99, which is the 1. Right. Literally, if you can remember minus 2 and plus 2, and minus 1 and plus 1, 95% and 68%, you can approximate anything you need if you do a little math. That's the normal and the standard normal. And the standard normal is still important because we have to go through it to get to something else. Remember the standard normal. Mean of 0, standard deviation of 1, 1 up, 1 down, 2 up, 2 down. And that's where all the deals with, here's the mean, here's the standard deviations. How many standard deviations up are you?